Let's see. All right, so obviously it's fictional. But last night I did find one of your students and I told him or her that they are patient zero. And they're going to infect, and when I say infect, they're going to say you are infected. They're going to infect 50% of the people they meet. If you find out that you're infected, you're going to do the same thing. You're going to become a secondary infection, you're going to be a host, and you're going to affect 50% of the people you meet. And at the end, we're going to see how many people in the room become infected. And we have a computer model that some of our computer scientists put together, and we're going to compare what did the model predict and what did actually happen, okay? So again, the instructions. Find somebody to talk with for 2 minutes. We might go a little faster just for time's sake. If you're told that you're infected, you're going to infect the next person you meet in 50%. If you meet someone who is also infected, you can, quote unquote, save that infection for the next person, okay? All right. Does that make sense? All right. Does that make sense, everyone? All right. So go. First round. Also, try to sit where you were sitting before we started the experiment. I'm sure you'll do that anyway. All right. It was pretty funny. I was kind of observing you while you were talking, and someone would say, oh, by the way, you're infected. Now people would go, yeah! So, I've never seen people so happy to be infected with Ebola. Actually, our patient Zero, and I told her last night, she was so ecstatic that she would be able to spread Ebola. So let's just kind of, I don't know if I can do an accurate count, but first, if you were infected, raise your hand. If you were. All right, if you were not, raise your hand. So I think the majority were infected. And so this, if you're wondering, the Ebola virus came here on the plane from San Diego. Can our patient Zero please stand up? There it is. There. So some of our computer scientists put together a model, and they want to, we talked about the parameters that we would have 10 rounds. And first of all, I don't know if it's going to work exactly because I don't know if everyone always heard me to switch off, so it may have not have spread as quickly as we predicted. But we assumed 10 rounds, people would pair up, they wouldn't pair up with the same person, and we did 2 different models that I'll show you, and we ran the simulation 10 times to predict how fast the Ebola virus would spread here in a room. So, all right, here we go. So there's 2 models that we ran. On one side, one model is where we assumed as part of the model that people would randomly find a partner to pair up with, that there was no deference to distance, that you might go across the room, that you might get someone near you. And the other model assumed that you instead would find the person closest to you, the nearest proximity. And so there's 2 graphs. The blue lines indicate different simulations that we ran. We ran it 10 times. Don will talk about this more stochastic model. We predict that every time the model is going to predict a different number of infected people. We ran it 10 times, and the orange line is the average. So in one scenario, we predicted 73 people would become infected. The other scenario, we predicted 34. And I just want you to put your thinking caps. Which model do you think was the one where there was no deference to distance, that was very random? All right, in the blue.
The left side would definitely be, I think, random because it can spread farther throughout the room. There's more chance to spread
Okay.
widely.
Okay. And then why? And then how about the, why on the right one would be proximity?
If you're, well, so if patient Zero is over there,
Mm-hmm.
and you stay close to yourself and you don't spread a lot. If you're right over here and you're not anywhere near the infected person, there's less chance of actually having higher numbers of infected people.
Do people agree with that? That's absolutely right. So at the left, we did a model, and we realized that this is the first model was on the left, and we realized that this probably won't happen. You're probably not going to just randomly traverse a room. You're going to find the person next to you, and so forth. And so we did another model where we said, all right, instead we'll have the agents find the person next to them, and it predicted 34, which probably, actually really it's kind of in between both of these of what we observed. Again, I think we had an issue where people weren't switching off at the same time. The model did exactly what we told it. I don't know if you did, but the model did. So I just want to show these two models. I have a little time. I'm going to try not to go over too much on Don's time here. See, is it displaying? All right, so this is a program in NetLogo that one of our computer scientists, Dilio, put together. And you can see my cursor? Yes. You can see down here we have a red person. So that's patient 0. And by the way, this is a program that's free. It's called NetLogo. It's from Northwestern, nearby. And I'm going to give you a link to both where you can find NetLogo, and also you can download this code that was developed. So the first time I want to show an example where we assume that when you choose a partner, you'll choose anybody. And we also have nearest as an option. So we'll do anybody, and we'll do setup, and we'll do one step. And what the model is doing is it's pulling people together. You can see that our patient 0 infected a person. And this is to simulate people clustering together. I'm going to speed it up, reset, and then I'm on this as a shortcut. Where's my mouse? There it is. Shortcut, I'm going to do 10 steps quickly. In this case, it predicted 65, and unfortunately, my mouse no longer is visible. Oh, no. Okay. Is it still there? Okay. So now I can see my mouse, so that's a good sign. All right, so again, this is also assuming 86 agents. We may have more people or less people in the room, so that's also going to skew it. So this setup, so 85, let's see here. So one simulation, 77, we'll do it again, see what it says again. 79, and this is what I did in my hotel room. I ran this over and over and over to come up with an average. All right, so 70. Let's do nearest. So setup. It's kind of interesting what happens here. 52. And notice it's clustering too. It's not diffusing throughout like in the old model. So there you go. And again, this is a code that you can download and you can play with and work around with. It was our best attempt to model what would happen in the room today. So, that's not it. Let's see, where is it? So obviously this icebreaker that we did today may not reflect what real life, in this instance, you're instantly infected when you talk to someone, and then you can instantly pass it on to someone else. That wouldn't occur in real life, obviously. Also, you never recovered from the disease. You were always infectious. No one had babies while you're here, so the population stayed the same. No one died. And also, the other thing that the model assumes is that you're going to randomly meet up with people, and that there's no influence of social networks. I think in real life, you're probably more likely to talk with your family and your friends. Here, we've kind of forced you to move to people that you didn't know, and that's probably not always typical. And the forced pairing, and then also no repeat contact. The model assumed that you would only talk to one person once, and you wouldn't talk to them again. Probably wouldn't happen in real life. You talk to people a couple times throughout the day. So I'm going to leave these here. I might give them to Felissa or leave them up here. It has the links to where you can find NetLogo. You can just Google or Bing NetLogo and you can find it. And again, you can take the code that we developed for the simulation, modify it, play with it, and see what you can do with it. And then our computer scientist Digley also put up on this website that's here, if you can write that down real fast. It's an applet on a website so that you don't have to download NetLogo to run it. Okay? Thank you so much. That was great. So I'm going to turn it over to Don from Pitt.